Next, we're going to talk about reactions that alkenes can undergo. Many of the reactions we're going to be seeing are described as electrophilic addition reactions. And one such reaction is the addition of HX across a double bond. So we call this a hydrohalogenation reaction, since we're adding a hydrogen and a halogen. For example, if we react an alkene with HBr, what's going to happen in these electrophilic addition reactions is we're going to break the pi bond, and then we're going to be able to add a group to each carbon. And we're going to see the same pattern again and again throughout this lecture. So when we're reacting with HBr, those are the two groups you're going to be adding, a hydrogen and a bromine. And you can see we have a choice on which carbon gets the hydrogen and which gets the bromine. It turns out that the hydrogen prefers to add to this end carbon, and the bromine goes to the middle carbon. So this is the only product that's formed. And just so we're clear on what's not happening, the other choice we could have made is that the hydrogen goes to the middle carbon and the bromine goes to the end carbon. And that product is not formed. So we described this reaction as being a regioselective reaction, since it reacts with just one region, one site preferentially. And this is a question of regiochemistry, when we see that there's more than one place that we can react and we need to make that decision. The regiochemistry that's shown is described as Markovnikov's addition, or we can call it Markovnikov's rule. And what Markovnikov's rule states is that the carbon with more hydrogens gets the hydrogen. The carbon with more hydrogens initially gets the hydrogen in the electrophilic addition. So we go back to our alkene. We see this carbon has just one hydrogen. The end carbon has two hydrogens. And so the hydrogen goes to the carbon with more hydrogens. And that's exactly what's observed. Now, if we want to understand why we follow Markovnikov's rule, we need to look at the mechanism. And it's a two-step mechanism. And it's going to start with our alkene reacting with HBr. What do we know about the reactivity of HBr? We know it's a very strong acid, and so in fact that's going to be our first step of the reaction, is our alkene is going to act as a base, HBr is going to act as an acid, and we're going to protonate that alkene as the very first step. Now, usually when we've done a protonation, it's been a lone pair on a base. Well, a pi bond can act as a base as well. We just start with that pi bond, those two electrons, attack the proton, kick off the Br-. So this is proton transfer as usual, two arrows, but we're starting from the pi bond in this case. And right now, and it's in this very first step, let's call this step 1. In this very first step, we have to decide which carbon gets the hydrogen. Now we know, based on the product observed, that the carbon goes to the hydrogen goes to the carbon with more hydrogens, the end carbon in this case. And what happens to this carbon? It just lost one of its bonds, so this carbon now has 1, 2, 3 bonds. If we do its electron count, we get 1, 2, 3. We know carbon wants 4. We end up with a positive charge on this carbon. So we're going to get a carbocation intermediate. And that's what happens when you protonate an alkene with an acid. You get a carbocation. Now let's think about that other possible regiochemistry. If I instead added the proton to the middle carbon, that would give me a carbocation on this end carbon. And now let's take a look at those two possible carbocation intermediates and think about why it is that this first carbocation is favored and leads to product, and the second carbocation is disfavored. Do we know anything about carbocation stability? How would you describe this one? It has 1, 2 carbon groups attached to the carbocation carbon. We call that a secondary carbocation. This is a primary carbocation, and we know the more alkyl groups donating into that carbocation, the better. So this is more stable. This primary is less stable. Primary carbocation is really awful looking, and so that's why this again is not formed. So we get this carbocation, and let's redraw it down here so we can do something else with it. What's going to happen to that carbocation? Well, it's now going to react with the Br- that was just formed in that first step. The carbocation acts as an electrophile. Looks like a great electrophile. It's got a full positive charge. It's electron deficient. The Br minus acts as a nucleophile, and we simply have the bromine bonding with the carbocation. And our reaction is done. We now have our addition product as we were expecting. We added H and Br across the pi bond, so it's a two-step mechanism. First we protonate, and then our nucleophile attacks adds to the carbocation. So considering that mechanism now, let's see if we can get a good understanding of why that Markovnikov's rule is followed. Okay, it turns out that Markovnikov addition is favored because that's the one that favors the more stable carbocation intermediate. It's all about the stability of the intermediate. If you have a more stable intermediate, that means it's lower in energy. And if it's lower in energy, if the intermediate is lower in energy, that means the transition state leading to that intermediate is lower in energy. That means the energy of activation is lower, leading to that transition state. There's a smaller hill to climb, and simply the reaction is faster. So what we're looking at here in the observed regiochemistry is kinetics in play. It's just simply which reaction is faster. In other words, it's not about product stability. So we don't look at the two possible regiochemistries and think, well, where would the bromine like to be? Is that interesting to us? No, it's simply about the stability of the carbocation intermediate. If we think about our reaction here, energy diagram, our starting materials are at some combined starting energy. Our products are typically going to be at a lower energy. Okay, and we have a pathway to get here. This is a two-step mechanism going through an intermediate. So our carbocation is going to be a high energy intermediate. We could put that here. And if this represents our secondary carbocation, the other path leading to the primary carbocation would be higher in energy. So these are the two possible paths that we can take. Our starting material can go to the secondary carbocation and then on to product, or the starting material can go up all the way to the primary carbocation and then down to the product. And if we look at these two paths and we ask which one is faster, it's going to be going from the starting material energy up to that transition state energy. My curve missed that a little bit. Here's our transition state. This is our energy of activation. Trying to go up to this transition state is going to be a larger hill to climb, so this is the faster reaction. Okay? And this part, formation of that carbocation, is going to be our difficult step. This is our rate determining step. It's going to be very difficult to lose that. To protonate and form the carbocation. That is an uphill battle, and so because this is a faster step, that means overall it's a faster reaction since it's a rate determining step. Okay, let's see an example. If you want to predict the product here, and I also pointed out that rather than just predicting the product, let's also think about the stereochemistry of that product. Okay, we have an alkene. We're reacting with HCl. So we're going to be breaking the pi bond. We're going to be adding a group to each carbon. We have a hydrogen and a chlorine. And where do you think the hydrogen should go? It wants to go to the carbon with more hydrogens. So we can think about our line drawing. We have one hydrogen here. We have two down here. So once again, the end carbon is going to be the place that we would want to put that hydrogen. And so this is our addition product. Now, that's our regiochemistry. How about the stereochemistry? What do you think? We have a chiral center here on this carbon. So what do you think the orientation of that chlorine is? Is it a wedge or a dash? Well, in fact, it's going to be a mixture of those. We could just draw it flat, but what we really mean is we're going to get some with the chlorine as a wedge and some with the chlorine as a dash. In fact, we're going to get exactly 1-to-1 of this mixture. What's the relationship of these two products? They are enantiomers of each other. So in other words, we're going to get at the racemate. Okay, and stereochemistry is going to be a big issue for us in looking at reactions of alkenes, because for alkenes we're starting out planar, we're starting out flat. So these are achiral starting materials. But when we break the pi bond and add something to it, we have the potential for creating new chiral centers in the new tetrahedral centers, sp3 hybridized centers that we're making. So stereochemistry is going to be an issue constantly. Okay, if we think about that protonation, we can protonate to form this carbocation intermediate. There's a hydrogen here. This carbocation intermediate is sp2. It is still planar, just like the alkene starting material. But now when the chlorine attacks this planar species, it can attack from the top face, attack from the top, or it can come in and Cl- from the bottom. So this is how we can get to either enantiomers. You can imagine your planar intermediate or your planar starting material, and attacking from one face or the other face is going to lead to your two possible stereocenters. Okay, so what we need to keep in mind here, what this is demonstrating, is that any new chiral center or chiral carbon is generated as both R and S, or with both R and S configurations. Okay, we have an achiral starting material, and so if we come up with a chiral product, we must get a racemic mixture. If we come up with a product that is chiral, it must be formed as a racemic mixture. So how do we normally draw this product? Well, we normally draw, it's assumed that we know it's a racemic mixture because that's always the case. And so we usually just draw it flat. We don't need to draw any stereochemistry here. Okay, but technically what this is representing is an equal mixture of both enantiomers. In some other examples where we create two new chiral centers in the addition to an alkene, we'll find that we're going to have to talk more about the relative stereochemistries of those two groups, and we'll see those in some of our next examples. Okay, what else can we add across a double bond? We can also add water across the double bond, so we call this the hydration of alkenes. We're going to break the pi bond, and what are the two groups that we're going to add to that pi bond if we're adding the components of water? We're going to be adding an H and an OH. So we're going to break this pi bond, we're going to add these two groups, and if you had to take a guess on where the hydrogen goes and where the OH goes, what if this followed Markovnikov's rule just like addition of HBr did, or HCl? Then we would expect the hydrogen to go to this N carbon, and guess what? That's exactly what happens. We add H and OH, and we get Markovnikov addition of the H and OH. So we started with an alkene, and we end up forming an alcohol product. So this is one way we can make alcohols, is by hydrating an alkene. Now our reaction conditions for this is we need water, of course, if we want to add water. And we also need acid. This is an acid catalyzed mechanism. And I just want to reflect for a moment on what happens when you take a strong acid like H2SO4 and you put it in water. What you end up with is H3O+. So sometimes your reaction conditions for this hydration might just show H3O+. Sometimes it'll show H2O in a strong acid. It can have a few different ways that it'll be presented. But if you ever see H3O+, it means that you have both HA, some strong acid, and H2O present. It implies that you have both of these. And the reason we can assume we have H3O+ is, by definition, a strong acid is something which fully dissociates in water. Dissociates in water. In other words, it's going to protonate water and give A-. So a strong acid, when we represent HA in aqueous conditions, if we ever use HA, what the strongest acid we have is going to be H3O+, the hydronium ion. You no longer have H2SO4 molecular in an aqueous solution. You have H3O plus, and you have the conjugate base of that strong acid. Okay, so when you see these reaction conditions, you can just go ahead and use H3O plus in your mechanisms, knowing that this is the mechanism by which that H3O plus was formed. So let's take a look at that mechanism. What do you think our first step should be in these clearly acidic reaction conditions? I think we need to protonate, and we can use our pi bond for that. Now I'm going to go ahead and draw out H3O plus since I know that's the acid in these reaction conditions. And so I'm going to have my alkene act as a base, and I'm going to protonate my pi bond. So just like our mechanism for addition of HBr, it starts the exact same way. It starts by protonating. And remember, this protonation step is the point at which we determine our regiochemistry, which carbon is going to get the H+. And just as a quick reminder then again, the other possibility is that we add the proton to the middle carbon. And if we do that, our carbocation ends up on the N carbon. So exactly like we saw for addition of HBr, we want to form the more stable, in this case, secondary carbocation. Always going to form the more stable carbocation. Every time we go to protonate an alkene, we'll keep that in mind. Okay, so we have a carbocation. Where do we go from here? We want to form this alcohol, so we need an oxygen to attack. How about using hydroxide? How about if we wanted to use hydroxide to add to the carbocation? Our mechanism would be finished very quickly there. But there's a problem with that. What's the problem with using hydroxide? Let's take a look at our reaction conditions. You expect to have a lot of hydroxide present in these strongly acidic conditions? No way. There is no hydroxide around. So who is our nucleophile? Who is the strongest nucleophile we have in these conditions? It's going to be water. Water is going to be the strongest nucleophile that we have and that we can use, and that is what's going to attack the carbocation. Okay, so let's think about this oxygen now that has just attacked. It still has 2 hydrogens on it. What else does it have? It still has 1 lone pair and a positive charge. So my water can attack. So we can call this second step attack of our nucleophile onto the carbocation. And we've added a group to each carbon, but we're not done yet because this oxygen has a positive charge. It's very unstable. We need to get rid of that positive charge. And how can we do that? Well, we know oxygen just wants to have 2 bonds and 2 lone pairs, so it's one of these protons that can be removed. So our last step is going to be deprotonate. So we call it when we remove a proton. And so what can we use to deprotonate? Well, we can come back and use this H3, this water that we just formed in our first step. And we're done. Okay, so a couple things we can note: that it is catalytic in acid. We need that acid there, but for every step where we protonate, there's a step where we deprotonate and get that H3O plus back. Okay, so we just need a tiny bit of acid to go along with our water. We could take a look at this pattern. It's going to be something we're going to see again and again with acid catalyzed reactions, where we protonate and then we attack and then we deprotonate. We're going to see that pattern again and again. And something else to keep in mind is that if this mechanism seems at all familiar, or these species that we have, it's because we've actually seen this mechanism before, but we've seen it in the reverse direction. We've seen it in the reverse direction. What do we call it when we take an alcohol and we lose water to go to an alkene? That's the dehydration of an alcohol. And how did we do that? We protonated to make it a good leaving group, and then it left, and then we deprotonated the carbocation. Okay, so same exact mechanism, same exact intermediates. When we compare the hydration for the dehydration, we'll we'll see that the hydration mechanism is the exact reverse of the dehydration, same number of steps. So we just saw this part. When we want to hydrate a pi bond, we use water and H2SO4 to go from an alkene to an alcohol. And how do we dehydrate? What conditions do we do to get rid of water? We use H2SO4 and heat. Very similar conditions in that they both have a strong acid. They both need acid, okay? But when we have, in the presence of water, we do hydration. We add water. So these reaction conditions are aqueous with some added acid. Where these conditions, look, we have H2SO4 heat. These are strong concentrated acid. Concentrated acid. So we have an absence of water. There's very little water. And that's how we do a dehydration. Of course, the heat also helps in doing the elimination. But take a look at your reaction conditions. They're very similar, but the key here is that we're adding water or removing water. But this is truly an equilibrium. You can force a reaction in either way by your reaction conditions, also by removing, having an excess of one or the other, or removing your product as it's formed. So let's try an example of this hydration reaction. We have an alkene, and we have H2O, H2SO4. So this looks like we're going to add water. We're going to add an H and an OH across the double bond. These looks like hydration conditions. And here's where we have our alkene. Okay, notice that these are not going to be reactions of benzene pi bonds. Benzene pi bonds are not alkene pi bonds. So all the reactions we're going to be studying in this lecture are not relevant to benzene rings, just isolated double bonds, separated double bonds. Now, what we have to decide is which carbon gets the hydrogen, which gets the OH. And we could think about Markovnikov's rule. Markovnikov's rule tells us that the more stable, the carbon with the more hydrogens gets the hydrogen. And that doesn't help us here, does it? Each of these carbons has just a single hydrogen. So you can see very quickly that Markovnikov's rule is only going to get us so far. It won't help us predict every case. So we need to have a better understanding of the mechanism and the foundation underneath Markovnikov's rule. And that foundation is the notion that in our mechanism we want to have the most stable carbocation intermediate. So in our first step we're going to protonate this pi bond, and that will give us a carbocation either here or here. So where is the better carbocation? Now how would you describe this carbocation in this position? Let's imagine the carbocation here. This is a secondary carbon, so it would be a secondary carbocation. That's not a bad one. How about if we had the carbocation in this position? It's also secondary. So again, we're seeing that we have very similar conditions, very similar situation. But this is not just secondary. We have this benzene ring here. And what do we call the position that's next to a benzene ring? We describe that as benzylic. So a carbocation in this position would be secondary, and benzylic, that's better than just being secondary. So we want to think about the stable carbocation. Okay, we want to know the mechanism and think about the mechanism, what's important to it. You might want to think, well, are sterics important in this case? Sterics have nothing to do with carbocation formation. That's if we're trying to do a backside attack maybe. But we really want to think about what is the governing thing in this situation. It's really about the carbocation stability. So what we want to form is the benzylic carbocation. And how do we get to the benzylic carbocation? What does that mean? That means we protonate in the other position. The hydrogen goes here so that the carbocation goes in the position we want. Okay, and this is resonance stabilized. Try it. That's a good exercise. Can you show the resonance stabilization of this benzylic carbocation? Okay, and so once we know the carbocation that's going to be formed, now we can go to the product, hopefully without doing a complete mechanism, because where the carbocation was is where our OH group will be added. Remember, adding an H and an OH, and in this case we'd want to put the OH on the benzylic carbon because that would be the more stable carbocation. Okay, notice I'm not showing any stereochemistry here. We did form a new chiral center, but we just know that's going to be racemic, so we could just draw them all as straight lines. Now, addition of H3O plus is one way to hydrate a pi bond and add the components of water across the pi bond. But there's two other alternative hydration methods that we're going to consider, and we'll see some benefits of that down the road. Okay, this first one is called oxymercuration demercuration, and as the name implies, it's a two-step process, and it's good to pay attention to the name of this because that's going to help us understand more about the mechanism and remember some of the details of this. Oxymercuration demercuration, and then it looks something like this. We start with an alkene. The first thing we do is we treat it with HgOAc2. That's called mercuric acetate. OAc represents the acetate group, so this is called mercuric acetate. And and water. We also add water in this step, and this adds a mercury group and an OH group. A little reminder: the AC group. Every time we see AC, it means we have COCH3. We have a carbonyl and CH3. So this is like an ester group here. So it breaks the pi bond and it adds a mercury and an OH. So that's our first step. And the second step, we treat this with NaBH4. That's called sodium borohydride. And it replaces the mercury part. It replaces the mercury with a hydrogen. We call this a reduction reaction because we're introducing hydrogen, we're increasing the number of CH bonds. And so sometimes actually this process is called oxymercuration reduction. Some textbooks might have it described as that process because the second step is both. It's a demercuration, we're getting rid of the mercury, and because we're replacing with a hydrogen, it's a reduction. So what happens here, we look at our structure, this mercuric acetate group gets replaced and it's just a hydrogen. So what happens as overall, let's look at the big picture comparing our starting material to our product. Overall, we broke the pi bond and we added two groups. We added an H and an OH. So this is a way of hydrating an alkene. And how would you describe the regiochemistry of that addition? Well, the hydrogen added to the carbon that already had a hydrogen, and so that's going to be described as Markovnikov addition. So this is an alternate way of doing Markovnikov addition. Now, why do we need an alternate way? Because we already have H3O+. Well, it turns out that this is going to be higher yielding, so in the laboratory this just works better than H3O+. There are a lot of other functional groups that react with H3O+ or might not be stable to those reaction conditions, so these are alternative reaction conditions. The mechanism does not involve a carbocation. We saw that H3O+ does, so that's going to be a benefit. It's not going to have any rearrangements in the reaction. So experimentally, this is a kind of a superior way to do the same thing, add water across the pi bond with Markovnikov regiochemistry. Let me just briefly show you this mechanism here. For this first step, the oxymercuration step, and we have our mercuric acetate. What happens is the pi bond attacks the mercury and kicks off one of the acetate groups, but then the mercury comes back and adds back into the pi bond to form a three-membered ring. And that gives a positive charge on the mercury. Now I'm showing you this because we're going to see some intermediates later in this chapter and in future chapters that look a lot like this. And so after we get a more thorough explanation of those species, you can come back and maybe have a better understanding of this species. Okay, but it turns out that this now gets attacked by the water and it chooses to attack on the carbon that's more substituted. Again, we're going to look at that in more detail later, but that opens up this three-membered ring to form the OH here and the HGOAC group here. Now, the other reason I want to point this out is because instead of doing this reaction in water, if we did this reaction in the presence of an alcohol as our solvent, then it could be the alcohol oxygen that opens up the mercurium ion, and we would end up forming an OR group. And what would happen if we did step 2 here, NaBH4, and replaced our mercury? We could get a product where instead of adding the components of water across the pi bond, we add the components of an alcohol across the pi bond. So this could be a way that we can make some ethers. Okay? Another possibility for adding water across the pi bond, our second one, is called a hydroboration oxidation. Now again, with that big name, that kind of tells us it's another two-step process. We start with an alkene. The first thing we do is we do a hydroboration. We add BH3. Now BH3 is in quotes because BH3 is a very unstable molecule. So what we're going to use are various reagents that are kind of the equivalent of BH3. We could use B2H6. It's called diborane, so this dimerizes, and that's a little more stable. Or we could have BH3THF, where the BH3 is complexed with a solvent molecule, a THF molecule. And so pretty much any boron reagent that you might see is all going to be doing the same reaction, and that is a hydroboration. We're going to be adding a hydrogen and a boron across the pi bond. Okay, our second step is an oxidation step. That means we're adding some oxidizing agent, and in this case what we typically use is hydrogen peroxide. And in our oxidation, we're going to replace the boron group with an OH. So our boron used to be here, and now there's an OH in that place. Hydroboration oxidation. So what did we do overall? We started with a pi bond. Now we have an alcohol. So what did we add across the pi bond? We added water across the pi bond. We added the H and the OH. How would you describe the regiochemistry of the H and the OH? The hydrogen went to this carbon. The hydrogen went to the carbon with less hydrogens. Would you describe that as Markovnikov addition? No, that would expect the hydrogen to add to the end carbon. So we describe this as anti-Markovnikov addition, anti-Markovnikov regiochemistry. And so this is kind of interesting because now it gives us a method we can use to get the opposite regiochemistry of the other methods. So let's take a look at the mechanism to see, again, a little bit of this mechanism so we understand where it goes, and some details of the product that unfolds. Okay, this first step, the hydroboration, is our first step. We had a hydrogen and a boron. This is a one-step mechanism, so we describe it as a concerted reaction. And we're going to form a bond from the hydrogen to the double bond, one end of the double bond, and the boron to the other end of the double bond. Both of these bonds are going to get added simultaneously. And our mechanism, our alkene acts as a nucleophile. That's electron-rich. And this boron acts as an electrophile. Boron, again, we talked about why it's so unstable. It's because a BH3 with just 3 sigma bonds has no lone pairs. It's missing an octet. It's highly electrophilic, highly reactive. So what happens is the pi bond attacks the boron and forms a bond here. But at the same time, the boron gives back one of its hydrogens and adds that back into the double bond. So we form these two arrows are moving these 4 electrons all at one time. And so our product then is we have a boron attached and we have a hydrogen attached. So this is going to explain two things. This is going to explain the regiochemistry. This is a regioselective reaction where the boron goes to the end carbon and the hydrogen goes to the middle carbon. Remember, we call this anti-Markovnikov. And there's a few explanations for this. One of them is just simply about sterics. Because the boron is bigger than the hydrogen, it prefers to go to the less hindered carbon. Okay? And there's also an electronic argument saying that, again, because this is the electrophile, as this bond breaks, it's better to have some positive charge building up on this carbon. So there's more than just a sterics argument here, but we can keep it simple by pointing to that. Okay, it turns out this reaction is also stereoselective. We describe it as being syn addition, and that's because since the boron and the hydrogen both added at the same time, they had to add to the same face of the alkene, and we call that syn addition when they come from the same side. They add at the same time to the same face, called syn addition. Okay, let's see an example then. If we wanted to do hydroboration oxidation on this alkene, okay, the first thing we're going to do is BH3THF. How do I interpret that reagent? I know I'm going to add a boron and a hydrogen. That's what all of our boron reagents are going to do. They're going to deliver a boron and a hydrogen. We're going to break the pi bond. We're going to add a group to each carbon. Now we have to decide where to add what. Is it going to follow Markovnikov or anti-Markovnikov? It's going to be anti-Markovnikov. The hydrogen is going to go to the carbon with less hydrogens. That's because this big boron, remember, that's going to be larger, and sterics plays a role here. The boron is going to prefer to go here. That's the regiochemistry. So remember, we're thinking about that. How about the stereochemistry? Because this is a concerted mechanism, they have to add to the same face. And so when we draw our product here, the way we can show them adding to the same face is, for example, we can draw them as both wedges. Now, if I add the hydrogen to the top face, what happens to this methyl group? This CH3 can no longer be in the plane anymore. This is a tetrahedrocarbon. That methyl group gets pushed back, gets pushed down. So it can add to the top face, or it can add to the bottom face. So it's your choice whether you want to show them both as wedges or both as dashes. Let's take a look at that other product where they're both dashes and see if they're the same thing. Sometimes they're going to be the same thing, sometimes they're not. So we'll have to evaluate each case. If they added to the bottom face, would this be the same intermediate product, or are they different? It looks like they're mirror images of each other. It looks like they're enantiomers. So we could either draw both of them, or we could just say plus enantiomer when we see that we've made a chiral product. This is because this is chiral, and we came from an achiral starting material. We know we can't just form this single chiral molecule. We always have to form its enantiomer as well. So we can either just say plus enantiomer, or we have to draw them both. Drawing both is usually takes a little too much time. Okay, so there's our hydroboration reaction: stereoselective, regioselective. Okay, and our next step is oxidation. And what we need to know is that this oxidation step retains the stereochemistry. So I'm not going to go through the mechanism for this oxidation on how it is that the boron gets replaced by the oxygen, but you can think of it as just inserting itself into the carbon-boron bond. So if it was a wedge, the oxygen will end up as a wedge. If it was a dash, it'll end up as a dash. So we'll draw that for our product here. What used to be a BH2 as a wedge is now an OH as a wedge. The other carbon stays the same. And plus enantiomer, of course. If you want to see what that enantiomer looks like, that's where both of our groups have been added as dashes. So an OH here and a hydrogen here. And the methyl group must be pushed into the wedge position, must be pushed up as the hydrogen added from the bottom face. Okay, so a couple things to point out. A racemate is formed. As always, now we have to be very careful to write plus enantiomer because we've added dashes and wedges to our product and we've drawn one specific enantiomer. Now we have to point out that the other enantiomer is also present. So we're going to keep that in mind and see lots of those examples in this unit. Okay, it's going to be anti-Markovnikov regiochemistry. So the hydrogen went to the more substituted carbon, the one with less hydrogens, and it needs to reflect syn addition of H and OH. So with the hydroboration oxidation, it's one of the most complicated reactions we'll be studying for alkenes because not only does it have complicated reagents that we have to take a look at, this BH3THF and this H2O2, but we also need to know what does it add, what is the stereochemistry, and what is the regiochemistry. Okay, let's, and here's an example. It's coming back to just what I pointed out. These are the questions we need to ask when it comes time to predicting a product. We have to interpret the reaction conditions, decide what the groups are adding, and then we have to decide where are they going and what's the stereochemistry. Where are we adding it is another way of asking what is the regiochemistry. And then what is the stereochemistry, dashes and wedges. So let's take a look at this two-step process. We're almost always going to be seeing those two steps back to back, so we're not so concerned about that intermediate product, what it looks like. We want to get in the habit of being able to draw a final product. So I see a boron here. This looks to me like hydroboration oxidation. Hydroboration oxidation. So we're going to be adding an H and an OH. This is one of our hydration reactions. Here's our two. We're going to break the pi bond. We're going to add a group to each carbon. We're going to add an H and an OH. And where should the hydrogen go? Because hydroboration oxidation is anti-Markovnikov, we want the hydrogen to go to the carbon with less hydrogens. This carbon has one hydrogen, this carbon has none, so that's a good place to do it. Again, if you kind of draw that exaggerated boron here, then that helps you remember that you want to avoid some sterics with it. And what is the stereochemistry? We need to do syn addition. So that means we can add them from the same face, either from the top or the bottom. That's your choice. But we need to show that in our product. So we can do that over here for where the boron adds. In our final product, we're not going to have a boron there. What are we going to have? We're going to have the OH. Where the boron goes is where the OH ends up. So we can draw that as a wedge right here. Now the trickier part, I think, is right here, the hydrogen. Where do we draw that hydrogen as a wedge? It's not correct to draw it down here because this is not what a tetrahedral carbon looks like. Okay, so let's try that again. This is our OH as a wedge. Where do we put a wedge on this carbon? The dash and wedge are pointing up in this direction. So remember, the H and the OH both came from the top face, but because we have a zigzag structure, they're kind of coming in from slightly different directions, and that's what our product should look like. What happens to this methyl group? He's no longer in the plane. He's being pushed back because we have a dash, so we must have a dash in that position. So being able to predict these products are going to draw on all that experience we have in drawing 3D structures and understanding tetrahedral carbons, and being able to draw something that represents the three-dimensional shape. So let's double check. We added an H and an OH. We added it with anti-Markovnikov regiochemistry. We added them syn. They're both wedges. Very nice. Is that my only product that I formed? That's going to be hard to do because this is a chiral product, and I started with an achiral starting material. So what's missing? We have to write plus enantiomer. Or we could say that it's racemic. We could say racemic if we want. We could either say plus enantiomer, or we could say racemic. Or some instructors do something like they say plus minus, indicating that we're getting that, a mixture of both isomers, both enantiomers, so we'll have no optical rotation. Either one of these is fine, but you have to do something. It's improper to draw a single chiral carbon as a product. Okay, a lot of textbooks get a little sloppy with this though, so try not to pick up on those bad habits. Okay, now again, why do we need to learn about all these different hydration methods? Well, it really comes to being synthetically useful. There's a very good reason that we need to be able to use these. Okay, one thing is that we can add water with either Markovnikov or anti-Markovnikov regiochemistry. So these are wonderful techniques that are complementary to each other and let us go in different directions synthetically. Okay. And these alternative methods have no carbocations in the mechanism, and therefore we have no rearrangements. And carbocations can do all sorts of weird things. So here's a perfect example. If we wanted to hydrate this alkene, and we just used plain old H3O+, you would not get the alcohol that you would normally expect, okay? Because it will rearrange. Try this. Try and do this. Try protonating, looking at the carbocation and see how it could rearrange. What we have is all these methyl groups over here, right next to where you'd have the carbocation. One of those methyl groups is going to shift over to give a more stable carbocation. Okay, so this is the case where if you wanted to hydrate this pi bond with Markovnikov regiochemistry, instead of using H3O+, you would do oxymercuration demercuration or oxymercuration reduction. And in doing that, because there's no carbocation and there's no possibility for rearrangement, you would get exactly the product you expect. Hydrogen goes to the end carbon, OH goes to the middle carbon. Perfect. Okay, or if you took the same alkene and you did hydroboration oxidation, then you would break the pi bond and you would add an H and an OH. But in this case, you would now do it with anti-Markovnikov regiochemistry, where the hydrogen goes to the inside carbon and the OH goes to the outside carbon. Okay, now why did I not, we know this is syn addition of the H and the OH, why did I not show any dashes and wedges in this particular case? I didn't show any dashes and wedges because neither of these is a chiral center. So there's only one stereoisomer that's possible here. It's not a chiral molecule, and there are no chiral centers. So in that case, there's no stereochemistry that needs to be shown. So it's only when both carbons involved are going to be forming as new chiral centers that we need to show the dashes and wedges and the configuration of those chiral centers. If we're not dealing with chiral centers, then stereochemistry is not so relevant. Now, how do we keep all of these reagents straight in our minds? Because this has just started. There's a lot more reagents to come, even in the reactions of alkenes. Well, let me give you just a little suggestion on how to use flashcards. I think flashcards are very useful for studying and learning organic chemistry, because it's a great way not only to organize your information, but to store it somewhere that's handy that you can refer to very quickly, and you can test yourself on the various information we're going to have for these chemical reactions. And so we're going to be seeing many, many, many reactions of this nature where we start with some kind of starting material and we react it with some sort of reagent or set of reagents, and it gives one or more products. Okay, we have these three possibilities. Okay, and one way that you can test the reaction is you can do you can have on one side your starting material and your reagents. So in other words, set up the reaction and make it like a predict the product. And then of course on the back you have the answer, and that's a way that you can test yourself to see whether or not you can do that problem. Okay, but that's not the only way that you can or should test yourself. Another way that you can test yourself is to say, okay, if I had this starting material and I wanted to go to this product, how could I do that? That's a transform type problem. Those are a little more challenging because now you have to plan what reagents and what reaction conditions are going to be necessary to do the mechanism that you want to employ. Okay, but that's still not the only possibility. You can also say, okay, well, given the following reagents and giving this as the product, what starting material did we start with in order to go there? And this kind of problem is going to be very useful as a way to test yourself and to organize, to remember as these number of reagents and reactions pile up and accumulate, you need to remember which functional group is associated with which reagent. So we just learned about hydroboration. We saw B2H6. You need to be able to associate B2H6 as a reaction of alkenes. and going to alcohols. So seeing it from all those directions is going to be very useful. I think managing information and developing those good study habits is one of the most important things that you get out of organic chemistry. So this lecture is a really good place to start thinking about those things. Okay, so what else can we add to double bonds? We saw addition of HBr, we saw addition of water. How about the addition of a halogen like Br2? Now, this is called the bromination reaction. We could also do chlorination. And it's described as anti-addition. And that's because when we react an alkene with Br2, it's common to see carbon tetrachloride as our reaction conditions. That's simply a solvent that's used in this reaction. So try not to let that distract you too much. It's the bromine that's doing the chemistry here. And what happens, as you might expect, is you break the pi bond. You add a group to each carbon, and for Br2, the two groups you're going to be adding is a bromine and a bromine. And what happens is the bromines end up adding to give the trans product only. So we get one up and one down. In the case of a cyclic compound, you can see that very nicely. Trans product. So we call the mechanism anti-addition, and we call the product trans. The opposite, let's see what's happening. We're not getting syn addition. We just saw an example of syn addition. Syn addition is what we called it when the groups add to the same face. So if they were both wedges, for example, that would give cis bromines, and that does not happen. Okay, so just getting to know some of this terminology, some of this vocabulary. Syn and anti describe the mechanism. Cis and trans describe the products that result from those mechanisms. Okay, now I showed it trans, so this bromine can be the wedge and this could be the dash, or the top bromine can be the wedge, dash, and this can be the wedge. Aren't these the same product? We're really going to have to keep making these decisions about stereochemistry again and again. What do you think? Is there any way you can flip one over and or rotate it, do anything to get them to superimpose? No, indeed, because this is a chiral compound. It has no plane of symmetry. Then these, in fact, are enantiomers. So we're going to get, as usual, we're going to get the racemate formed here. You don't have to draw both. You could draw just one and say racemic or plus enantiomer. Just for argument's sake, let's think about this syn addition product. If I added these bromines to the same face, added them to the top, let's say, would I also have to add them to the bottom? Would that be a unique product? Is it right to say plus enantiomer here? Actually not in this case, because if I added the bromines to the bottom face, it would be the exact same product. The difference here is because this is a meso compound, it is symmetrical, it is achiral, so it does not have an enantiomer. So we're really going to have to keep this in mind. It's not enough to just go through as you're doing predict the product and say plus enantiomer, plus enantiomer, plus enantiomer. You need to be thoughtful about that and think about it. Okay, so back to the bromination. What we observe is anti-addition, so we'll end up with these trans bromines. Okay, so we describe this as a stereo-specific reaction, and we get one specific stereochemistry. And if we want to understand why we get this anti-addition, we're, as usual, going to have to look at the mechanism. So let's do that. The bromination mechanism starts with our two ingredients. We have an alkene and we have bromine. And what we can imagine happening is the alkene acting as a nucleophile, the bromine acting as an electrophile, and so you could have the double bond attack the bromine, attack one bromine and kick the other bromine off. Now let's see what that would give us. That would attach a bromine to one carbon, and that would form a carbocation on the other carbon. So kind of like protonating a double bond gives a carbocation, adding a Br plus to an alkene also can give a carbocation. However, this is not formed because this is less stable than another arrangement this can have. Because this bromine has these lone pairs, those lone pairs can come back in and can instead form a three-membered ring. So this bromine has 2 bonds and still has 2 lone pairs. It's an unusual looking bromine, right? We're used to it having just 1 bond. So let's think about the formal charge for this bromine. We have 1, 2, 3, 4, 5, 6. Bromine wants 7, so it's missing an electron, so this is a Br+. And this is called a bromonium ion. And that is actually the intermediate that we get in the bromination reaction. So we don't form this carbocation. Instead, we add the bromine, the Br+, to both carbons of the double bond to form this bromonium ion. And it turns out that the reactivity for the bromonium ion involves each of these carbons. They are partially positive, and that makes them electrophilic. Those are electrophiles. Those are electrophilic carbons. And so we'll see what happens to those next. Okay, so just this is an introduction to the bromonium ion. Let's step back and look at the complete. So when we want to start the bromination mechanism from the beginning again, we have our alkene, we have our bromine, and we know that every time we have bromine in the presence of an alkene, we're going to go to this bromonium ion. Now, I am actually drawing this as a wedge. They're both bonds are pointing in the same direction. We know we're going to get this bromonium ion, and so how do we get there? Well, the mechanism involves both the double bond coming out and attacking the bromine and kicking off the bromine, so like we thought was going to happen in the first place. But at the same time, one of the lone pairs of this bromine adds back in to the second carbon of the double bond. So we end up forming 2 bonds to the double bond in one step of the mechanism, and that's why they end up adding to the same face. That's why we're showing them both, in this case, as wedges. Okay, this is an electrophile. Do we have any nucleophiles around in the reaction? Well, sure, we just formed in this very first step, we formed Br-. And so this Br- is going to attack the bromonium ion, and it will attack either one of these carbons. And we can show it attack this one, and if it attacks that carbon, what happens is it treats this carbon-bromine bond as a very good leaving group, and it opens up that bromonium ion ring. Now, what does this mechanism look like? Have we ever seen a mechanism where a nucleophile attacks a leaving group, attacks a carbon and kicks off a leaving group? In a single step, attacks a carbon and kicks off a leaving group? Absolutely, this is the SN2. So we describe that as backside attack, right? So if my bromonium ion is a wedge, if it's sticking out at you, where does that second bromine have to come in? Has to come in from the opposite side, has to come in from the back. So if it attacks this carbon on the right, then that new bromine is going to be a wedge, and that original bromine is still here now with its 3 lone pairs, and it's back to being neutral. Okay, so we can call that path A if you want, product A. Or we could have it attack the other carbon and do an SN2 on that carbon, path B, and that's how you can see we can get to our other enantiomer. If we attack that carbon, then this carbon would be the one, bromine would be the one that's back, and this one would be out. So we get our 1-to-1 mixture of enantiomers. Okay, so it explains the backside attack is why we get the anti-addition. Because whatever face the first bromine added to form the bromonium ion, the second bromine has to come in from that opposite face. So we always get anti-addition, 1 up and 1 down. Now it's possible to add more than just Br2 in this fashion. We can have other nucleophiles add to the bromonium ion in something that's known as forming a halohydron. And the example here would be as if we had an alkene reacting with not just bromine, but bromine in water, or maybe bromine in an alcohol. Okay, what happens in that case? Well, we form the bromonium ion, but instead of the Br- attacking it, it's the water that's going to attack it. And so the 2 groups we end up adding will be a Br and an OH instead of 2 BRs. Okay, this is called a bromohydron. When you have a BR and an OH, it's called a bromohydron or halohydron as a general term. Okay, but as we're going to get trans stereochemistry again, it'll still be anti-addition. And of course, we have to say plus enantiomer because it was totally random that I chose to make the bromine a wedge and the OH a dash. So the other one will also be formed. Okay, let's think about a mechanism. How do we combine these 3 ingredients to make this bromohydron? Okay, the first thing that's going to be happening is this bromine is going to be reacting with the alkene. So like I said, anytime you see bromine and alkene, we know we're going to form the bromonium ion. I think it really helps to draw the bromonium ion that we're expecting. A lot of times we draw it as a wedge. You could draw it as a dash if you want, but this is often how we see it. So I know this is the bromonium ion I'm going to get. I'm going to be adding a bromine Br plus to one face of the alkene, and so that helps me draw my mechanism. This pi bond is going to attack one bromine, kick off the other bromine, and then that first bromine takes its lone pair and adds back in to form the second bond. So now you can see there's still 2 lone pairs left. One lone pair has gone to form this bond, and the pi bond has gone to form this bond. There's our bromonium ion. Okay, so we have an electrophile with a bromonium ion. We look around for a nucleophile. What nucleophiles do we see? Well, we have water as a nucleophile, and we have Br minus as a nucleophile. Now, who do you think would be a better nucleophile? I see a negative charge with this bromine. I think he would be a very good nucleophile. However, what we're looking at here is a matter of statistics, because water is our solvent, and water is surrounding all these molecules, including the bromine molecule, the bromine atom. Right? It's solvated. It's totally surrounded by water. So statistically, as is this bromonium ion, statistically the nucleophile that's going to be most likely to attack and therefore leading to our major product is going to be the water instead. So water does, in fact, when you have water present, water will be the most significant nucleophile to attack. Again, SN2 mechanism, so we have our backside attack, and it will come in as a dash then. The bromine on this left-hand carbon is still here. He's still a wedge. With 3 lone pairs now, he's neutral. And what do we have on the other carbon? We have an oxygen bonded in the back position, in the dash position. And what else is on this oxygen? We still have our 2 hydrogens, and we still have 1 lone pair, and we have a plus charge. So we formed a bromonium ion, and we attacked the bromonium ion. Okay, is our mechanism done yet? Once again, anytime we use water as a nucleophile, our mechanism isn't done until we get rid of that positive charge. How do we get rid of that positive charge? We can deprotonate. Okay, you can use anything you'd like. Some books use Br minus to be nice and tidy, but really, again, because water is our solvent and water is surrounding everything, that is going to be the most prevalent base that we have. And so we can deprotonate, and then we're done. In our mechanism, we usually show the mechanism just to get one of the enantiomers, knowing that we would have the same mechanism with the opposite stereochemistry to get the other enantiomer. So we can alter our reaction conditions a little bit, put in a solvent that could be nucleophilic. This is a new nucleophile that we're adding in here, and therefore when we form a bromonium ion, it's going to be that solvent that attacks to give a halohydron. Now, because we're adding 2 different groups across the double bond, we need to think about regiochemistry again. In other words, which carbon gets the bromine, which one gets the OH. And the regiochemistry that's observed is shown here. The major product formed is the one on the top here, where the OH goes on the middle carbon and the bromine goes on the end carbon, and the other product is not formed. So we need to explore this a little more to understand why this would be the major product that's formed. And in order to do that, we need to look at our bromonium ion intermediate. Both of these products would come from the same bromonium ion. Here's our bromonium ion. Our only question is, when water attacks this bromonium ion, where does it prefer to go? So in order to answer this question, let's take a look at the transition state. Let's imagine that water attacking here and starting to form a bond, starting to open up the bromonium ion ring. So let's show those as partial bonds. As that carbon-bromine bond stretches, the positive charge on the bromine is now being shared with the carbon, and we have a partial plus on the bromine and a partial plus on the carbon that's being attacked by the nucleophile. Or we could have the nucleophile attack this carbon, and our partial plus will be on the bromine and this carbon. Okay, so if you take a look at these two transition states and we try and decide which one is more favorable, which one is going to be a faster reaction again, we take a look at the location of this partial positive charge. How would you describe the carbon bearing this partial positive charge? It's attached to two other carbons, so this is a secondary partial positive, and in this case, on the end carbon, it's a primary partial positive. So just like we know for carbocation stability, we're going to extend that same logic to our partial positives here, and we'll acknowledge that the secondary partial positive is better, it's more stable, and therefore it's a lower energy transition state. Okay, so when the water goes to attack this bromonium ion and has to decide between these two positions, it's actually going to attack the carbon that's more highly substituted. Because this carbon, let me write this down here, this has it's more partial positive, so it's the better electrophile. And that means the nucleophile adds here. So the water does not add to this end carbon, it's drawn to the more substituted carbon because that has more of a partial positive. Now what's interesting about this is our mechanism is an SN2, right? It's attacking this carbon and breaking open the ring. But it's an SN2, but it's going to the more substituted, more sterically crowded site. So it's not just a simple SN2. We describe this as an SN2 with some SN1 character. And the reason it has some SN1 character is because of the positive charge. Because we do not have just a neutral electrophile being attacked. It's not a plain old SN2. Because there's a positive charge on the leaving group, electronics beat the sterics. Electronics win over the sterics. So even though it's more sterically crowded, the partial positive character, the electron deficient character is significant enough that that's where the nucleophile goes in spite of the increased sterics. Okay, so that explains our regiochemistry then. The nucleophile goes to the more substituted carbon. Okay, we can't really describe this as Markovnikov or anti-Markovnikov because we're not adding a hydrogen, but this is similar to Markovnikov rule that we've seen. Although we're not adding an H plus in our mechanism, we are effectively adding a Br plus. And so just like the H plus prefers to go to the carbon with more hydrogens, the Br plus prefers to ultimately end up there as well. Br plus goes to carbon with more hydrogens, just like H plus did. Okay, so hopefully you can see, you can tie it in a little bit with the addition of HBr or the addition of water. Those mechanisms had carbocation intermediates, so there we were looking at competing carbocations. Here, because they both of these have the same bromonium ion intermediate, there's only one intermediate. What we're looking at is the path from that intermediate to the product, who is going through the lower energy transition state, and therefore that's the faster reaction. So slightly different explanations, but still they have some similarities. Okay, let's try and predict the product here. How about if we reacted this alkene with bromine and methanol as our reaction conditions? Bromine and CH3, Br2 and CH3OH. Again, what are the questions we need to ask? What are we adding? Now, if all we had was Br2, then we add a bromine and a bromine. But because we have a solvent that can be a nucleophile, it will be a nucleophile. So the two groups we're adding are going to be Br and what do we get if CH3OH was our nucleophile? Would we add the OH group? No, we get an OH if we use water. We get the OCH3 group when we have an alcohol. We add the OR group. So in this case with methanol we get the methoxy group. Okay, where are we adding it? That's our regiochemistry. So we're breaking the pi bond, we're adding a group to each carbon. Which one gets the bromine, which gets the OCH3? We need to consider that. We need to think about the stereochemistry. What is the relative stereochemistry of those two things? And for that we need to understand the mechanism. And that's going to tell us the relationship of those two. Let's look at some choices for our products and see if we can decide. Okay, so we said we're going to add a Br and an OCH3 to these two positions. Let's take a look at those choices. Okay, all of these are chiral, so they all should say plus enantiomer. So these, assuming these are all racemic, which one has the proper combination of the regiochemistry and the stereochemistry? First of all, the stereochemistry. Let's think about our mechanism. We go through a bromonium ion. So the bromine adds to one face, and then our nucleophile, our methanol, comes in from the opposite face. Remember, it is anti-addition. Anytime we have bromonium ion, we have to get anti-addition. So which are the ones that have anti-addition? Here are OCH3 and our bromine added to the same face. Right? That's syn addition. Here, the bromine and the OCH3 added to the same face. That's also syn addition. So I know those answers are wrong. Okay, but here the bromine is a dash and the OCH3 is a wedge. That's good. Here, same thing. Bromine is a wedge and the OCH3 is a dash. Perfect. So these are both anti-addition. They have the stereochemistry right. How about the regiochemistry? When we make this bromonium ion, let's imagine that. Let's imagine that bromonium ion. Let's do a little work here to think about that. And the methanol is coming in and attacking. Where is it going to go? Is it going to be governed by sterics? No, it's going to be governed by the positive charge in this case because this carbon is tertiary. It has a higher partial positive, and so the nucleophile goes to the more substituted carbon of the bromonium ion. So which product is that? Looks like D is our best product because it has the proper regiochemistry as well. The methoxy went to the carbon that was tertiary. Interesting again, an SN2 happening on a tertiary center. This is not an ordinary SN2. It's definitely because of that charge that we're seeing that SN1 character and we're allowing this to happen. Very good. Another reaction we can have for alkenes is one called catalytic hydrogenation. And as the name implies, hydrogenation, we're adding hydrogen across the double bond. We will break the pi bond and we add two hydrogens. What you can see here from this example is that the hydrogens have both added from the top face. So we describe that as syn addition. We describe the hydrogens in the product as being cis to one another. The reaction needs a catalyst. That's why we usually call it catalytic hydrogenation. We'll talk about catalysts in just a second. It's considered a reduction reaction, okay, and that's because we are increasing the number of CH bonds. We're increasing the number of CH bonds, so that's going to be a reduction. And overall, it's an exothermic reaction. Like most of the addition reactions we're seeing for alkenes, this is exothermic. It's releasing energy. And that's because overall, we are breaking a weak pi bond and forming a stronger sigma bond. So all these addition reactions are going to be favorable because overall the net change is breaking of a pi bond and forming stronger sigma bonds. So that's usually good news. Okay, let's talk about the catalyst a little bit, what's going on here. We have some kind of metal catalyst that's going to provide a surface upon which this reaction can happen. It's going to speed up the reaction. And what happens is the metal absorbs the hydrogen gas. The metal also grabs onto the alkene, and then the metal delivers the hydrogens to that alkene. And in doing so, it delivers them to the same face. It delivers them to just a single face, and that's why we get syn addition. The hydrogens end up on the same face of that, whichever face of the alkene it goes to. Okay, our catalyst can be described as either heterogeneous catalyst or homogeneous catalyst. The heterogeneous catalyst, the ones we see most often, you'll see palladium, 9 times out of 10 as the complete reaction conditions for catalytic hydrogenation. And these are metals that are added into the mixture. They don't dissolve in the solvent, so we just stir them very rapidly, or we shake the bottle maybe, because they don't dissolve, and so we need some way to mix them in with the gas and with the alkenes that's dissolved in the solution. And then in the end of the reaction, you just filter the catalyst off, and you can isolate your product. Okay, the other class of compounds are called homogeneous catalysts. They are called homogeneous because the reaction mixture in these cases are homogeneous. They're a solution. They don't have any solids in there because they do dissolve in organic solvents. And that's because these are organometallic species. They have both organic components attached to the metal. We have a variety of transition metals like rhodium or ruthenium or iridium, and they have various organic ligands attached to them. So this guy is called rhodium triphenylphosphine chloride. So it's got each of these phosphorus has 3 phenyl groups, has 3 benzene rings attached to it, and then there's 3 of those coordinated around the rhodium. So a lot of benzene rings in there, and that makes it organic, soluble, and so we could use organic solvents. We're called homogeneous that way. And by varying the ligands that we have here, you can have a huge variety of catalysts, and you can do some cool things with that. You can have some increased selectivity. For example, if you have a diene, if you have 2 alkenes in a structure, you could use this catalyst to just reduce the, you could just react with the less hindered alkene, for example. It would be sensitive to sterics in that case. So you can't really do that with catalytic hydrogenation with just ordinary catalysts. That just reduces every pi bond it sees. But we can do some more interesting things with the organometallic catalysts. So we might see some of those too. Now the heat of hydrogenation of this reaction is going to be useful to us, and it can tell us something about the stability of the alkene starting material that we had. So for example, if we take a look at these series of alkenes, 1-butene, cis-2-butene, and trans-2-butene. Okay, what's interesting about this series of alkenes, if we take either of these alkenes, any of these alkenes, and you react them with hydrogen and palladium, you'll break the pi bond, you'll add hydrogen to each carbon, and the product you're going to get is the same in every case. You're going to get butane. So this is an interesting series of compounds to study because they all give the same product with the same energy at the end of the reaction. We can study we can measure the heat of that reaction, and we see it here given in kcals per mole, minus 30, minus 28.6, minus 27.6. We see a difference in there in the energy given off, and this is going to be related to the stability of the alkenes. Now we already know something about the stability of these alkenes, right? Which of these do you think is going to be the least stable? We know that the less substituted an alkene is, the less stable it is, and so we know that the terminal monosubstituted is going to be the least stable. These are both disubstituted, and of the disubstituted, who's the most stable? The trans is the most stable. And the fact that these energies are going in this trend is a reflection of that. We can show a diagram here to show how we can relate the heat of hydrogenation data. If we take a look at our alkene A, we know is higher in energy than alkene B, which is higher in energy than alkene C. Okay, but when they get hydrogenated, they all go to the same place. They all go to butane as the final product. They end up with the same final energy. So to go from A to butene is a longer path than to go to B or to go to C. So because A starts out as the least stable, the highest energy, it gives off the most heat when it's hydrogenated. And so that's why this number is the biggest number. Where C, because it's the most stable, it starts out at the lowest energy, it does not have as much heat to give off when the hydrogenation takes place. So we should be able to, if given some heat of hydrogenation data, we should be able to convert that, interpret that into something about the stability of our starting alkenes, of the alkenes that we're comparing. This is also useful when we're looking at dienes. So if we had two double bonds, what are the relationships we can have for those two double bonds? There's three possible relationships they can have. They can have one where they share a carbon. They're right on top of each other, right next to each other. We call these cumulated systems. The p orbitals on that middle carbon, because it's sp hybridized, the p orbitals on that carbon are orthogonal. The p orbitals for the first double bond are perpendicular, orthogonal to the p orbitals for the second double bond. We can have double bonds that are unrelated to each other. We call those isolated pi bonds, because we have these pi bonds here and these p orbitals and these p orbitals, and because of this sp3 center in between, there's no relationship to them. Or we could have conjugated pi bonds, and that means that the p orbitals on the first double bond nicely align with the p orbitals on the second double bond. When we have conjugated, it means we have a pi and then a sigma and then a pi, like that. And that allows for overlap. It allows for resonance. And can we see that in our heat of hydrogenation data? Absolutely. When we have these isolated pi bonds, we get about 60 kcals of energy taken off. That's approximately the heat of hydrogenation for an alkene, for an ordinary alkene, times 2. An alkene was somewhere around 30 kcals, and so an isolated pi bond, we get about 60 kcals because we have twice as many pi bonds to hydrogenate, to react. Okay, but when we force those double bonds to be cumulated to each other, it actually increases the amount of energy given off for hydrogenation. That tells us that that arrangement now is less stable. This is the least stable of all three of these. It destabilizes. Putting those two pi bonds perpendicular to each other destabilizes the pi bonds. Where putting them in a conjugated relationship actually stabilizes it. This is the most stable, and that's because of that resonance. So we can use the heat of hydrogenation data to get some evidence that we are, which arrangement of double bonds is more or less stable. And what I forgot to point out is these are all pentadienes. And so again, if we have excess hydrogen and palladium, if you have as much hydrogen as you need, you will reduce every pi bond there is and convert it to an alkane, and we will get just pentane as our final product. So it's useful to study this series because they all go to the same product. So we can do this same cartoon again. For our energy diagram, the accumulated pi bonds are unstable or less stable than an ordinary diene, and having them conjugated is more stable than an ordinary diene. They all go to pentane as their final product, and A has the highest distance to go, and B and C has the lowest distance to go. So this minus 54.1, the smaller the number, the smaller the magnitude of it. They're all going to be negative. Remember, this is always going to be an exothermic reaction. But the smaller that magnitude tells us the lower in energy our alkene or diene started before we did the hydrogenation. Okay, let's see if we can predict a product here. If we reacted this alkene with H2 and catalyst, okay? One thing I wanted to point out with this example is here we have a carbonyl. And a carbonyl has a pi bond, but it's not a carbon-carbon double bond, and so there's no reaction here. Catalytic hydrogenation is a reaction for alkenes, carbon-carbon pi bonds. We'll see it for alkynes also when there's a triple bond. Okay, so we'll leave that carbonyl there. We can draw our backbone. This is kind of our carbon chain. And so we're adding hydrogens, and do we know anything about the stereochemistry of that addition? Regiochemistry is not an issue, of course, because we're adding a hydrogen and a hydrogen. So there's no decision to make there. But how about the stereochemistry? Let's think about that mechanism of the catalytic hydrogenation. The hydrogen's bound to the metal, and it's going to be delivered to the same face of the alkene. So we get syn addition. So how do we draw those hydrogens coming from the same face? We could draw them both as wedges, or we could draw them both as dashes. So if there are wedges, that means for the zigzag down, our wedge is pointing down, but for the zigzag up, our wedge is pointing up. So here they're coming from the same face, all from the top. And what does that do to these two methyl groups? That pushes them back into the plane. Okay, so it's your choice on which carbon part of the chain you want to keep in the plane, but you want to make sure that the other one gets pushed from being in the plane. It's no longer in the plane. This is a chiral product, so we want to make sure we say plus enantiomer, or we say racemic, so that we know that having the hydrogens come from the bottom face will give a different product, and that product is also formed, the enantiomer. Okay, another way we can draw this, there's a lot of different ways to draw this, so it's important to keep that in mind when you compare your answer that you've worked on to the answer in the textbook or the solutions manual, that if there's a slightly different, you need to be able to evaluate whether your answer is still right or not, or if you've done something wrong. Okay, another possibility is we can say, okay, I want them to both come from the top face and pointing down here. For example, okay, we could do that. That would keep this first carbon the same, but this second carbon, the bond if the wedge is down here, then the bond that's in the plane is this methyl group is still in the plane, and it's the ethyl group that got pushed down to behind the board or behind the screen. So a lot of different ways that you can draw this, but get into something that you're comfortable with, and that, again, with a lot of practice, you are used to drawing these chiral products in these new stereocenters that are going to be formed when we form new chiral centers in addition reactions. The next group of reactions we're going to look at are called oxidation reactions, and there's several ways that we can oxidize an alkene. First, though, let's take a look at that word oxidation. We know it comes hand in hand with reduction. We've learned about redox reactions in the past, but in organic chemistry, we view it a little differently. It's a little easier to see than some of the redox reactions that you may have seen in general chemistry. So let's just take a look at organic examples of oxidation and reduction reactions. And let's just look at a one-carbon species. Every carbon has 4 bonds, so we have this example where with methane, all 4 bonds are to hydrogen, and then we replace one of those bonds with an oxygen. This is methanol. And then we replace 2 of those bonds with oxygen. This is formaldehyde. And then we could have 3 bonds to oxygen. This is formic acid. And then finally, all 4 bonds can be to carbon. To oxygen. This is carbon dioxide. So we've gone from 4 bonds to hydrogen, and one by one we're replacing the number of a hydrogen bond with an oxygen bond. This process in going from left to right is described as an oxidation. All these are oxidations. So, for example, you could say that methanol can be oxidized to formic acid, to formaldehyde, or even it can be oxidized to formic acid. And the way that we can identify it as an oxidation is we are increasing the number of CO bonds while decreasing the number of CH bonds. So any process that trades a CH bond for a CO bond, we know is an oxidation. And as a result, the oxidation number will increase. Okay, but we don't have to calculate the oxidation state of each carbon in order to make that determination. It really can be done visually by looking at the oxygens. Okay, this reverse process and going from right to left, these are all described as reductions. And what happens in a reduction is we have an increase in the number of CH bonds. And at the same time, there's a few different things that can happen. In this case, we're seeing a decrease in the number of CO bonds. Okay, other bonds can be lost instead. In general, as soon as we're increasing our number of CH bonds, then we're going to see it as a reduction reaction. Kind of like catalytic hydrogenation, we call it as a reduction reaction. Okay, and as a result, by increasing those CHs, our oxidation number of the carbon will go down, will be reduced, just like in a reduction reaction. So it's not changing the definition of a redox reaction. We're still having a change in our oxidation state, but we're just going to look at it a little more simple in this case. Okay, and there's going to be three, as you can see, there's going to be three types of oxidation reactions we're going to be studying for alkenes. This first one will give as a product, we break the carbon-carbon double bond and we put in its place a three-membered ring with an oxygen in it. This is known as an epoxide. It's called an epoxide when you have a three-membered ring with an oxygen, and that's one possible oxidation. If you react a double bond with K-4, what happens is you break the pi bond and you add an OH to both carbons. That forms a diol or a glycol. It could be called a glycol if you have two OHs on right next to each other, or a vicinal diol. Or you can react with ozone, a reaction called ozonolysis, and in that reaction we actually break the carbon-carbon double bond and we replace it with carbon-oxygen double bonds. And we get these carbonyl products. So we're going to get either ketones or aldehydes or some combinations of those, depending on what your substitution patterns were on the original alkene. Okay, so a handful of new reagents, very different looking products, but do you see why these are all grouped together and all described as oxidation reactions? Right, in each case, you've lost carbon-carbon bonds, and what have you replaced them with? Carbon-oxygen bonds, carbon-oxygen bonds, carbon-oxygen bonds. You are increasing the content of oxygen in your structure, and we call that an oxidation. So let's look at our first one, the epoxidation reaction. If we take an alkene, like we said, and we react it with this guy, we'll define that in a minute. It's called a peroxy acid. The product we get is an epoxide, and we're going to add both of those CO bonds from the same face. We call that syn addition. Now, I've drawn both of those bonds as wedges. I added the oxygen from the top face. What if I added it from the bottom face? Is that another product? Do I say plus enantiomer here? Would it be a unique product if I drew both of those bonds as dashes? Or would it be just the same thing flipped over? Same thing flipped over. So because this is a meso compound, it has no enantiomer. This is an achiral product, so this would be a case where we just draw the stereochemistry as either wedges or dashes, and then we're done. We don't have to say plus enantiomer. It would be wrong to say plus enantiomer. Okay, let's take a look at this formula, RCO3H. It looks very similar to a formula we may have seen before, RCO2H. RCO2H, when you expand that, you have a carbonyl and an OH. That's a carboxylic acid. Okay, and that's kind of an ordinary compound. We'll study its reactions down the road, but as the name implies, it's just an acid. It's not an oxidizing agent. But now the formula we're looking at is RCO3H. So just by looking at the formula and recognizing that it deviates from the carboxylic acid, it has extra oxygen in it, that should tip you off to the fact that it must be an oxidizing agent. It must be something that causes oxidations. Okay, and so let's look at that structure. It still has a carbonyl, but now it has two oxygens. And this is described as a peroxy acid. This oxygen-oxygen bond is called a peroxide. And this is very unstable. This is dying to get rid of an oxygen. Very easy to cleave that bond. And so that's what leads to its reactivity and the fact that it is possible to oxidize things. Okay, another example of a peroxide is this guy, H2O2. What's that called? That's called hydrogen peroxide. This is another oxidizing agent, and this in fact would also work to do this epoxidation reaction. That would work just fine because you still have that peroxy group. And look at the formula, H2O2. It's got an extra oxygen compared to water, which is nice and stable. So this is now instead a strong oxidizing agent. Okay, so we might just draw a peroxide. We might draw a generic formula like RCO3H to know that we're dealing with a peroxide. Or we could pick a specific peroxide reagent. One that's very commonly used is this guy. He's called meta-chloro. Meta describes the relationship between these two groups, that they're 1,3. We've got a chloro and we've got a peroxybenzoic acid. So without this double oxygen, this would be benzoic acid. But because it has the extra oxygen, we call it peroxybenzoic acid. And luckily, we can abbreviate this guy as MCPBA. So MCPBA stands for metachloroperoxybenzoic acid. If we saw the formula, what part of the formula would clue you in that this is an oxidizing agent? Right there, that extra oxygen. If we saw the name, we need to just recognize the name. Very common to just use the acronym here. So again, another great flashcard to get to know MCPBA. Okay, and just a general mechanism. And for the most part, we're not going to be studying detailed mechanisms for these oxidation reactions because they're kind of outside of the scope of our organic chemistry mechanisms. But I want to give you a little bit of an idea of what the mechanism is, so it's not just this total magical black box thing. And what happens by having these two oxygens attached to one another and having this acetate group here is we have a leaving group attached to an oxygen. Very unusual. That's again what makes it such a great oxidizing agent. And what happens is the pi bond of the alkene attacks the carbon and kicks out the leaving group. But at the same time, this lone pair adds back in and forms the three-membered ring. So we saw this similar mechanism with for the oxymercuration forming the mercurium ion. We saw this with Br2 to form the bromonium ion. In this case, we're seeing that this would be a way to form a three-membered ring with oxygen, and not as an intermediate, but as a final product. Okay, so this mechanism happens again because it is concerted, because both of those bonds happen in a single step. That's why they must come from the same face. We get syn addition. It's concerted, so we have syn addition. Let's look at another way that we can make an epoxide. What would happen if we took an alkene and we reacted with bromine and water? Well, I know that bromine always makes that bromonium ion. So would this add a bromine and a bromine? Or do we have to pay attention to this water here as our solvent? We do, in fact, because that's going to win over the bromine, the Br minus, as what gets to attack the bromonium ion. So this is going to add a Br and an OH across the pi bond. And what about the stereochemistry of those two groups? Again, because we know the bromonium ion is the intermediate, that means if the bromine comes from the top face, the water must come from the bottom face to do that backside attack for the SN2 to open up the bromonium ion. So we can show anti-addition, is what we call it. So we're going to get the OH and the Br trans to each other, plus an enantiomer. Doesn't matter who you draw as a wedge and who you draw as a dash. Okay, we saw this reaction as a way to make bromohydrons. Well, what I want to show now is there's a nice application for bromohydrons. If I took this structure and I treat it with sodium hydroxide, what can happen? Well, sodium hydroxide is a base. It's a nucleophile, right? So you might think, well, maybe we could do some substitution elimination. Well, base anytime you see something that's a base, we want to look first to see, is there any place that it can act as a base? Is there any proton that is unusually acidic? Well, and sure enough, we have an OH group here, so in the presence of base, we're going to deprotonate some of that alcohol group to make an O-. And what can happen here is now we have a great nucleophile, very strong nucleophile in a structure where we also have a leaving group. And so what can happen is that nucleophile can attack the carbon and kick off the leaving group. Okay, and so this is an SN, this is an intramolecular SN2, if you want to call it that. It's a backside attack. And those are possible, and we've usually seen it just for 5 or 6 membered rings, but 3 membered rings are possible too. And now we're seeing that if we did that here, we would get a product we call an epoxide. So what's nice about this synthetic scheme is it kind of relies on some newer reactions we've seen with addition reactions to alkenes, and some older reactions we've seen where we're doing a substitution of a good nucleophile on a carbon-bearing leaving group. Why might I use this instead of just using MCPBA or some other oxidizing agent? Well, maybe I have some other functional groups on this molecule that are sensitive to oxidizing agents, so it might not be suitable to do an oxidation reaction, but I could still convert the alkene to an epoxide by doing electrophilic addition and then a base-promoted substitution reaction. The next oxidation reaction we'll study is dihydroxylation. Dihydroxylation means that we are adding 2 hydroxyl groups to the alkene, and the way we do that is with either KMNO4 as a reagent or OSO4 as our reagent. Either of these, you can see the similarity in their structures. We've got a metal with 4 oxygens on it, and in fact, our reaction conditions are usually more complicated. They have some other additives in there, some other oxidizing agents. But these are the key ingredients we need to see that will tell us we're doing a dihydroxylation. And what we do is we break the pi bond, and we add an OH to each group, and this turns out to also be a syn addition. We get syn addition of 2 OHs. So we call this a dihydroxylation, a syn dihydroxylation, meaning the OHs end up cis to each other. Any enantiomer in this case? I drew the OHs both as wedges. How about if I drew them both as dashes? Would that be the same compound, or would that be a different one? Well, I don't see any plane of symmetry in this molecule. This is a chiral molecule, so that means it must have an enantiomer. And this is a case where we'd want to say plus enantiomer. Okay, so how do those 2 OHs get added in a syn fashion? Again, just a little bit of a mechanism to give you some background on that, not a detailed mechanism. But if you think of this potassium permanganate or the osmium tetroxide, if you think of either of these reagents as some metal with 4 oxygens, what's going to happen is that metal is going to take 2 of those oxygens and add them at the same time to the double bond. So it's going to be another concerted mechanism. We're going to form this bond and this bond all in one step. So our mechanism looks something like this. We form a bond here, this pi bond moves, this pi bond moves, something like that. And because they're adding in the same step, the oxygens have to add to the same face. So it's concerted. It goes via a cyclic intermediate, so when we follow our electrons around, we get something like this. Again, the exact details of the metal species is not important because it's going to vary whether it's manganese or osmium. Okay, but the idea is we've added them in one step, and that's why we must get syn addition. So kind of like the epoxidation, and the any concerted mechanism is going to give you that syn addition. Okay, how does this get to this? How do we end up with the 2 hydroxyl groups? Well, again, we do some kind of workup. We cleave off the metal and we free those oxygens to be OHs. But again, this carbon-oxygen bond is now set, and the stereochemistry is fixed. Okay, and finally, let's talk about ozonolysis. This is our third oxidation reaction. As the name implies, it uses ozone. And let's take a look at this ozonolysis. We have two words here. The ozone tells us that we're using O3 as our reagent. And what does lysis mean? What does it mean to lyse something or to cleave it? It means we're breaking apart. So we're going to be breaking or cleaving the molecule with ozone. So just knowing the word ozonolysis, knowing the name of this reaction is going to help you predict the product properly. Okay, but first let's talk about ozone just for a second, because we've all heard of ozone before. It's kind of interesting that we're using it as a reagent in the lab. And the question I want to ask is, do you think ozone is something that's good or something that's bad? Kind of has a dual nature. Okay. We know that there's an ozone layer, and we're very concerned that there's a hole in the ozone layer. So that kind of lets us know that ozone is a good thing, and the destruction of ozone is a bad thing. And so that's true that ozone can be good, and that's when it's in the stratosphere. So when it is, that's the layer of the atmosphere, the outermost layer that's kind of protecting us from outer space, and that's because what the ozone does is it absorbs UV radiation. So the sun is coming down with a ton of this ultraviolet radiation, and the ozone layer is doing a good job of absorbing a lot of that, so only a fraction of that makes it down to Earth. That's a very good thing, because this radiation is meaning it's coming from sunlight, I should say. Okay, and that's a good thing, because this UV radiation is damaging. It can do damage to your skin. That's what gives you a sunburn. That's what causes, at the simplest cases, it's a sunburn, but you can also damage DNA if it penetrates. You can have damage there, cause skin cancer, and so on. So I'll put that here too. So the more UV we have coming down to Earth, the worse shape we are. So the ozone is very good for that. It's protecting the Earth, and we don't want to put anything in there that might destroy the ozone. Okay, but it's bad. Ozone is something that's bad when it's in the atmosphere. So in other words, if that's something that is surrounding the Earth, if it's something that I'm interacting with, then ozone is not a good thing. This is it acts as an irritant to your mucous membranes and so on. It's a smog component. It's one of the parts of smog that is tracked in the for health alerts and that sort of thing, because it can cause irritation in your nose and your eyes and that sort of thing. Okay. It also, we're seeing it's an oxidizing agent, so it is a very strong oxidizing agent. So if we have a lot of ozone around, then that can do a lot of damage to just materials that we have that might have double bonds in them. We're seeing that it reacts with double bonds, and so obviously ozone will do that rapidly. Now, just the oxygen in the air is also an oxidizing agent and can cause some of these damaging reactions, but ozone is even more reactive and will do it more rapidly. For example, if you ever taken a rubber band and tied up some bills or something and thrown it in the attic or thrown it in a box and stored it for a while in your closet, what happens when you go back to that box a year down the road and you take that thing that was strapped to the rubber band? What happens to the rubber band sometimes? Have you ever seen it just crumble or crack or fall apart or become stiff, something like that? That is an example of oxidation that's happening to it, where it's breaking down the structure of the rubber. Okay, so we can have oxidation reactions like rubber bands, for example, or your tires on your car, they'll crack, they'll wear because of oxidation reactions and so on. Okay, so what we have is we have a little ozonizer, we have a little instrument that we can bring in the lab, and it generates a stream of ozone gas. So you stick that into your reaction, you can bubble some ozone through it, and we can cause this oxidation reaction to occur. So let's see what happens at the molecular level when it reacts to the double bond. What's going to happen when it reacts with ozone, again, not doing a detailed mechanism here, but just giving you some idea, is we're going to completely cleave all bonds between the two carbons. So the two carbons used to have two bonds connecting them. The ozone inserts 3 oxygens in between the carbons, so the two carbons are no longer connected. This is known as an ozonide intermediate, and that's always formed as your first step in an ozonolysis, and that's why there's always a second step in an ozonolysis reaction. It's always followed up by some other set of reagents. These are typical ones we might see, like zinc or dimethyl sulfide. These are reducing agents, and so this is known as a reductive workup. And what happens is we simply take these carbons. So this carbon has 2 separate bonds to oxygen. After our workup, we're just going to put both those bonds to a single oxygen. This carbon has 2 bonds to oxygen. After workup, we're going to have 2 bonds to a single oxygen. And that's all. With this reductive workup, there was a hydrogen here. There was a hydrogen that started out all along, and that hydrogen is going to remain in our product. Depending on the type of workup you have, that might change. Sometimes we could do an oxidative workup where we get rid of that hydrogen. But this is kind of the typical procedure we'll see for ozonolysis, where we react step 1 with ozone and step 2 with some kind of reducing agent. And so our products, how do we predict our products? We completely break the carbon-carbon double bond, and we replace the carbon-carbon double bond with a carbonyl at each position. We insert a CO double bond called a carbonyl. So in this case, we got 1 ketone and 1 aldehyde. We describe it as an aldehyde if it has a hydrogen attached to it. But we'll get a mixture of ketones and aldehydes depending on what alkene we started with. Let's look at a few examples of predicting the products of ozonolysis. So again, let's looking at our reaction conditions and trying to decide what to expect here. I see ozone. There's exactly one reaction we know that uses ozone, and that is ozonolysis. So right there in the name, we find out what we're doing to this molecule. We're finding our double bond, and we're completely breaking that double bond. When we go to draw the products then, we'll now have 2 separate products. We've broken our molecule into 2 pieces. We're going to have a carbonyl on the 5-membered ring, and we're going to have a carbonyl. You can leave it upside down. You don't have to flip it over. It's fine to kind of leave it in the orientation it had. We're going to have a carbonyl with this 3-carbon chain. One great check that you can do when you're doing an ozonolysis is to take a look at your starting material. I had 8 carbons in my starting material, and when I'm done, I should still have 8 carbons. And I do. I broke it up into a 5-carbon ketone and a 3-carbon ketone. Okay, because ozonolysis will take every double bond in a structure and break it. And so if you have multiple double bonds, you'll end up with lots of fragments for your product mixture. In fact, ozonolysis is a nice way to study the structure of a compound, is by breaking all the double bonds and studying the fragments that you get. You can help determine where the double bonds were located in your structure. Those are some good exercises too, is looking at ozonolysis products and putting them back together. How would we do that in this case? That's a good problem. If you said that these were the ozonolysis products, and you were asked what is the starting material that gave these products, how would you approach that reaction? Well, you know that ozonolysis forms carbonyls from carbon-carbon double bonds, so we're going to take those 2 carbonyls and we're going to reattach them. We're going to reattach them as double bonds to each other. Okay, so take a look for some of those problems. Those are good exercises as well. How about this one where we have a double bond within a ring? How is that going to affect our product? Okay, again, ozonolysis and zinc reductive workup. Looks pretty typical. Here's the double bond that we're going to be breaking. But now, because we're cleaving a ring, we're going to cause the ring to open up. This is a really good idea to number our carbons so we don't get lost. And what I recommend actually as a good way to handle some of these problems is to redraw your starting material with your carbons numbered 1, 2, 3, 4, 5, 6, and then literally erasing the bond that you're breaking. See, that way I know that I haven't lost any carbons or gained any carbons. I'm breaking that double bond, and what am I replacing it with? a carbonyl at carbon 1, and a carbonyl at carbon 6. Okay, you don't have to straighten it out and draw it as a nice zigzag line. You can leave it in whatever conformation you want. Now the only thing I'll point out here though is because I made an aldehyde, it's okay to leave your line drawing like this, but by convention we usually draw in the hydrogen of an aldehyde. That's the only hydrogen attached to a carbon that we normally leave in a line drawing. So I'm just going to feel a little more comfortable adding those hydrogens in because that looks a little better to me rather than having a carbonyl dangling at the end of the chain. But that is optional. So even though they weren't shown on carbons 1 and 6, of course there's a hydrogen here and a hydrogen here. So those are still preserved with our reductive workup for the ozonolysis. Finally, let's look at some additions to alkenes that follow a completely different mechanism, and that is a radical mechanism. So let's kind of think back to what we know about radical reactions. The one reaction that we've seen before is the free radical halogenation of alkanes. We take an alkane and we react it with bromine and light, for example, and we would form an alkyl halide. What we're doing is we're taking our alkane, we're plucking off a hydrogen, and we're replacing it with a bromine. We call that free radical halogenation. So let's review the mechanism for that so that we can kind of look at a new radical mechanism. The very first step in any radical mechanism is some kind of initiation, something that forms radicals. In this case, the reaction, the exposure of Br2 to light, to H nu, we represent it that way, causes homolytic cleavage of that bromine-bromine bond, where we split it and one electron goes to each bromine. So we're going to form a radical. We're going to form two of these. We're going to form two bromine atoms. That's our initiation. And then what that bromine does is a hydrogen atom abstraction. It's going to look for a hydrogen on the alkane to remove. It's going to remove the one that results in the most stable radical possible. So I'm going to go for one of these internal ones rather than one of these end ones. And what an atom abstraction looks like is you break the carbon-hydrogen bond. One electron pairs up with the radical. The other electron stays behind. So we just formed a molecule of HBr. In fact, I forgot to write up here, that's the other product you get in free radical halogenation. I usually am more concerned with the organic product, but you're also forming HBr here. And the other product we get is this secondary radical. What does this radical do? Same thing, atom abstraction. That's what radicals do. So in this case, it's going to go after bromine. It's going to take a molecule of bromine, and it's going to do a bromine atom abstraction. And we're going to, just like we did before, break this bromine-bromine bond. One electron pairs up with the radical. The other electron stays behind. So that's how we get our product. That's our bromination product. And the other thing we formed here was Br dot. So what was nice about this radical reaction is it also reformed the bromine dot, which can come back and do another hydrogen atom abstraction, and so on and so on. You could say etc. here. So we get this chain reaction mechanism that started with the initiation. Okay, and that's because the steps that we have, the majority of the steps that are taken in any radical mechanism are described as propagation steps. We start with one radical, it reacts with some stable species, and then as a result we get a new radical. So here we had a Br dot reacting with an alkane that gave an alkyl radical, and then we had an alkyl radical reacting with Br2 to give a bromine radical. Okay, it's propagating because one radical begets a new radical. Okay, and there's two general types of propagation steps we can have. In free radical halogenation, the only one we saw was this first one, for example, atom abstraction. So the radical comes after an atom from a stable molecule, such as a hydrogen atom, and it removes that hydrogen. Okay, we saw it can pluck off a hydrogen, it can pluck off a bromine from Br2. We're going to make a molecule here of a hydrogen attached to the radical, and we're going to form a carbon radical in this case. Okay, so free radical halogenation relies on only atom abstraction as our propagation steps. Okay, but if you happen to have an alkene around, a carbon-carbon double bond, there's another propagation step that can happen, and that's called addition to an alkene. And what does it look like? Well, a radical comes in, and it's the pi bond that breaks. One electron pairs up with the radical, and the other electron stays behind. So let's take a look at that product. What's happened now is this radical has bonded to the alkene and formed a radical where the pi bond used to be. So we call this an addition to an alkene. And so, since we're studying reactions of alkenes, let's take a look at some examples of radical additions to alkenes and see what those products look like. The most common reaction to study in the first place is the addition of HBr. And we've already seen, let's review the reaction we've already seen. And that's addition of HBr. Just normally what happens is we break the pi bond, we add an H and a Br, and we do it with Markovnikov regiochemistry. This is our electrophilic addition, and we saw that mechanism. That mechanism was protonation with our acid and then addition of Br minus. Okay, but if we do this reaction in the presence of ROOR, which is the formula for some kind of peroxide, a different mechanism occurs, which is a radical mechanism, and as a result of that mechanism, we get this product, which has the bromine on the end carbon and the hydrogen on the middle carbon. We describe that as anti-Markovnikov. So it's possible to add HBr with Markovnikov regiochemistry or anti-Markovnikov regiochemistry, and we control that by whether or not we've added in some peroxides. Okay, so let's see how this mechanism works, the radical mechanism works, and why is it that we get the anti-Markovnikov product. Okay, as usual, our reaction has to start somewhere. We have to initiate a radical. Okay, that's the job of the peroxide. This is a radical initiator, and it's this oxygen-oxygen bond that's so weak and just loves to dissociate, cleave homolytically, and form two radicals, alkoxy radicals in this case. Okay, now we have a source of radicals now, and our reaction conditions are we have an alkene and we have HBr. So what this radical is going to do is it's going to do a hydrogen atom abstraction on HBr and pluck off a hydrogen to give Br dot. And so ultimately the result of this reaction of HBr with peroxides is we're forming bromine radical. We're forming some Br dot. And how is that Br dot going to interact with the alkene? Well, if we have an alkene around, it can add to that alkene. We have a 4-carbon alkene here. We're going to break the pi bond. One electron joins up with the radical. The other electron stays behind. So the bromine adds and forms a radical. Okay, and this is the step at which the regiochemistry has been determined. The first group you add has to go to one carbon or the other, so that's when you decide the regiochemistry. So let's look at the choice that we have to make. The bromine can add to the end carbon, or the bromine can add to the middle carbon, and that would give the radical over here. So let's look at our two possible intermediates, our competing intermediates, and decide which one is better and why. Well, radical stability turns out has the same general order as carbocation stability. So if we take a look at this secondary one and this primary one, we'll see that the secondary is going to be favored. Okay, so just like we've seen before, we're going to follow the path that gives the more stable radical intermediate. Okay, so that's important, and it turns out that because radicals are not quite as unstable as carbocations, this is not the only issue that's going on here. So it turns out that it's also nice that the Br dot adds to the less hindered carbon. So for this radical reaction, actually steric hindrance does play a little bit more in it than it would for just the addition of HBr with their electrophilic addition mechanism. But either way, we can see that the bromine wants to add to the end carbon. we now have this radical. How do we get to our product? We wanted to add HBr, so let's come back and redraw our radical. What can that radical do to get to the final product? We only have two choices. It can either do an atom abstraction or it can add to an alkene. And because we have plenty of HBr around, it's going to choose to do an atom abstraction. It's going to pluck a hydrogen atom off of HBr. And we just formed our product. And what else do we generate in this step? We just generated some more Br dot. And he can continue to come back and add to a new radical and so on. So once again, these propagation steps go on and on and on. This is the way that we make our product, is we start with a radical and then we make a new radical and we keep going and keep going and keep going. So we saw that we have some techniques to add water across a pi bond with Markovnikov or anti-Markovnikov regiochemistry, so that's very important. And now we can see we can do the same thing with the addition of HBr. We can add it with Markovnikov or anti-Markovnikov by adding some peroxides to our reaction mixture. Let's take a look at one more interesting reaction that's radical, has a radical mechanism involving alkenes. And that is the idea of doing a polymerization starting with an alkene. This molecule is called vinyl chloride because it's got a chlorine attached to a vinyl group. It's attached directly to a double bond. This is described as a monomer because it's just a single unit. If you added some kind of radical initiator, then we would expect that initiator to add into the alkene and form a radical. Now let's suppose that in these reaction conditions, all we have is this monomer. All we have is vinyl chloride, a ton of vinyl chloride, just a tiny little bit of radical initiator to get a radical mechanism going. What product do we expect to have happen here, to observe here? Well, we have this radical, and if this has plenty of vinyl chloride around, then this new radical is going to do another addition to an alkene. So now we have 2 units of vinyl chloride here. We call this a dimer because we have 2 of them. And if we still had vinyl chloride around, then this could continue to add, break the pi bond, and we could get a trimer and a tetramer and so on, and it can continue going until we get a polymer, many, many, many repeating units. And so this is how one of the ways that polymers can be built is by counting on this radical chain reaction. And we can see here that we have a repeating unit. This is what we see. We see our vinyl chloride components, right, at 2 carbons with a chlorine on there. And depending on the monomer that we start with, we can get a different polymer each time. And depending on what groups are attached, then we can get very different properties. This is PVC. This is polyvinyl chloride. It's used for water piping, for example, for sprinkler lines, that kind of thing is PVC piping. But a wide variety of fabrics and plastics and materials that we can get from this polymerization reaction. It's also possible to do this same sort of polymerization reaction with an acid catalyst, because if we form a carbocation in the presence of lots of other alkenes, then that alkene can act as a nucleophile and so on, giving a new carbocation, which then can add to another carbocation, and so on. That would be another way of doing a polymerization, but radical mechanisms are very well suited for that as well.